Yes, very good afternoon to all. Today, our topic is the delta to star and star to delta transformations. Actually, this technique, that is delta to star and star to delta conversion technique, is used in the electrical networks to simplify. Basically, we are having different types of simplification techniques. The first simplification technique is the usage of theorems. Okay, we can use the maximum power transfer theorem, we can use Thevenin's theorem, we can use Norton's theorem, and sometimes in order to find the response, we can use the superposition. So this start in the same manner. If we want to find the response or current in any particular branch, we can use the current division rule or voltage division rule or any other mentioned techniques. But some cases, either of any of these techniques may not be applicable. In such cases, these two, that is delta to star or star to delta conversion techniques, are very very helpful. Now, in this today's class, we will see about this transformation techniques in detail. So, first of all, let us consider a two circuits. So these two circuits, the first circuit is the delta connected network. As the name indicates, the three elements of a circuit are connected in delta fashion between the three terminals A, B, C. So the element which is connected between the A and B is designated as RAB. Similarly, RBC and RCA are connected between B to C and C to A respectively. The same equivalent circuit, actually these three terminals should not be changed. The three terminals A and B, the, between these three terminals, the network can also be connected in a star fashion, that is inverted Y or Y, okay, like that. So let us assume that these two are equivalent circuits. Equivalent circuits means between the terminals A, B, and C, whatever present, that will be equivalent from here first diagram to the second diagram. Okay, that means whatever is connected to A and whatever is connected to this particular A terminal, B terminal, and C terminal, in between these three terminals, the circuit is same, that is the delta is equivalent to star. Now, how to convert it? That is a question. Let us designate the element connected to the terminal A is RA, and the element connected to B is RB, and element connected to C is RC. So, as in here, in the star connection, there is some common point is there, that is in general known as a neutral. But whereas in the delta connection, there is no common point. Okay, so next. Now, first we will see the how to convert from delta to star. For example, if we were given a delta connected resistances, then how to connect into the equivalent star? We will see that procedure. Let us assume that between the A and B terminals, consider the equivalent circuit. And we are also assuming that nothing is connected to C while dealing with A and B. While dealing with A and B, nothing is connected to C outside. Then what will happen? C is not connected to anything here, and C is not connected to anything in the star also. Then what is the equivalent between A and B? The equivalent between A and B is the wherever nothing is connected to C terminal outside, then RBC and RCA will be in series. Then that series combination will be in parallel with RAB. So that is indicated here. This RHS of first equation. And second one, in the star connection, if nothing is connected to C, no current will be flowing through this. Then the resistance effect RC will not be there. So RA and RB will be simply in series. So whenever we are considering an equivalent circuit between A and B, when C is open circuited outside, so that means C is not connected to anything. Then RA plus RB, the RA plus RB, okay, is equal to RA plus RB is the in the star connection between A and B terminals. And in the delta connection between A and B terminals, what is the equivalent RAB in parallel with RBC and RCA combination. Okay, so now if we equate these two, then we will get the equation 2. RA plus RB is equal to RAB into RBC plus RCA divided by RAB plus RBC plus RCA. Clear? So in the similar manner, we can develop the equations for between B and C terminals. If we consider B and C terminals, we need to consider nothing is connected to A outside. In that case, RB and RC, that is RB plus RC, is equal to RBC in parallel with the series combination of RAB and RCA. Okay, that is just indicated in the next diagram. Similarly, if we see the terminals A and C, if we see the terminals A and C, if nothing is connected to B outside, then let us assume that these two are equivalent, that is delta and star are equivalent, then RA plus RC is equal to this RC in parallel with this particular two combination. So we are getting three equations, the equation 2, equation 3 and equation 4. Now, if we do some type of simplification technique, for example, if we take 2 minus 3, then what will happen? If we take 2 minus 3, then RA minus RC will be there. Okay, so that will be become one equation. Now, if with that equation RA minus RC, if it is clubbed with the fourth equation, then we will get 2 RA. Then RA value will be obtained. So that is a simplification technique. Now, if we do that simplification, then what happens is the star connected network, the star connected element RA is given by the product of RAB, RCA divided by the sum of the three resistances in delta. Okay. Similarly, RB is given by RBC. RB is star connected element to the terminal B. So RAB, RBC should be multiplied and divided by the sum of these three resistors. Similarly, RC is equal to RCA, RBC divided by RAB, RBC, RCA. So how to remember these things? Actually, if we do the simplification, we are getting. Then in order to remember that, we can remember by means of this particular technique. So this is simply just like a sign. So if delta is given to you, you want to obtain a star, then any star connected arm is given by the adjacent sides product of the elements divided by the sum of all elements in the delta connection. Okay, this is delta to star transformation. So next, if we are given a star network and if we want to connect it to the delta, then how to do it? Same equations we are taking, that is 1, 2, 3, 4, 5, 6, 7. These equations only to be taken. Now, in this one, what we are doing is we are dividing 5 by 6. If we are dividing 5 by 6, what will happen? What will get? RA divided by RB is equal to RAB gets cancelled and denominator gets cancelled. You are getting RCA divided by RBC. Okay, so that one, similarly, if we divide by the if we divide 6 by 7, then RB divided by RC is equal to, you will get RAB divided by RAC divided by, That is, denominators will get cancelled. Now, if we do that type of divisions, and similarly, this if you divide by 5 by 6, we will obtain this one. So from this, we can say we can write that RCA is equal to RA RB RA divided by RB into RBC. Similarly, if we take 5 by 7, we will get RAB is equal to RA RBC divided by RC. So these equations are known as the auxiliary equations. These auxiliary equations, okay, so if we substitute auxiliary equations 9 and 11 into 5, then what we'll get is RBC is equal to RB plus RC plus RB RC divided by RA. You will get like this. Okay. Similarly, the case for the RAB, RCA. So we had obtained certain type of equations. How to remember equations? Here, the thing we are considering is the star to delta conversion. The star network elements are given to you, and we need to convert it into the equivalent delta network. So, if we see that, A is there, the delta element between A and B, or A and C. If we see the delta element A and B, that is given by the sum of the two arms connected to A and B in star connection divided by plus the product of these two divided by opposite side of resistance. So that technique is, you can remember like this. Resistance between two terminals of delta is equal to sum of the resistances connected to those terminals plus product of the same two resistances divided by the third side. Okay. So here what you are doing is star is given to you. You need to convert into delta. For example, RCA. RCA is obtained by RA plus RC plus RARC divided by RB, opposite side. So in this manner, this is the technique you can remember. Okay. Now we will see say, a small example so that you can better understand. Now in this example, you are supposed to calculate the current in branch EF. What is the normal technique? We can apply the mesh analysis, or we can apply the nodal analysis. Okay. Or we can apply the Thevenin's theorem, or we can apply Norton's theorem. But here, a simple technique, these three, 500, 200, 200, these three are in delta. Now, if you connect these three into equivalent star, then you will get this 500, 200. What is the star connection? Star connection is equal to 500 into 200 divided by 500, 200 plus 200. You will get 111.11 ohms. Similarly, this side also you will get the same. That is delta to star conversion. You need to apply the formulas for delta to star connection. These formulas you need to apply. Okay. So now, if we connect, what about this terminal C? The C terminal will be connected to one more resistor in star connection. That resistance value is equal to 200 into 200 divided by 200 plus 200 plus 500. You will get 44.44 ohms. Okay. Now, in this case, an additional point or node is created. That is known as a neutral point in the star connection. Now, if you observe the resistance between N and D, it will be simply a combination of these two, 44.44 plus 600. And similarly, the resistance between N and F will be equivalent of N to G and A to F. Clear? So next, once we got this type of element, once you got this type of thing, so what you will get, you need, what is our aim? Our aim is to calculate the current in this EF branch. Okay, so but what is this EF branch total resistance from N to F? It will be 1111 point ohms plus 600. Clear? And that is in parallel with 44.44 plus 600. Now, if these two are in parallel, these two are in parallel, so the total resistance in the circuit is this A to N plus N to D. So now it will become 338. That is this particular this particular uh, portion between the N, this particular portion between N to E. Okay, this will be, so this portion will be replaced by an equivalent. So in this one, the 600, the 600 ohms and 111.11, these two are in series. That is in parallel with 44.44 plus 600. Now, these two simplified total resistance between this N to D is nothing but 338 ohms. So now the total current flowing through A is given by total voltage divided by total resistance. Total voltage divided by total resistance. Clear? You will get a current, total current is equal to 0.222 amperes. 0.222 amperes. Now, once you got this particular current, you can apply here the current division rule. You can apply here the current division rule. In order to calculate the current through the EF, that is NG and EF, you need to take the total current into opposite side, this one, divided by these two sum. So that will be seen in this particular slide. So if you do like that, if you apply the current division rule, sorry, if you apply the current division rule, then you will get the current through this branch is given by 0.1055 amperes. Now this is one of the example problem. Clear? Similarly, this is one more example where you are given some combination. You need to obtain the equivalent resistance between A and B. First of all, see this. This you need to assign some points. Already points were given in the question if it is okay. Then otherwise you need to create. So GFD. In between them, the circuit is delta connected. You can convert it into the star. Okay, that is one technique. One more technique is these three, that is 8 ohms, 1 ohms, and 4 ohms. These three are in star. You can convert it into the delta. That is another technique. So you can use any technique, but you need to go for the simplified one. You need to go for the simplified one. If you consider the points between GDF, GDE, okay, if you consider the points between uh, GDE, yeah, GDE. So you will have 3 ohms, and E. F is in middle. GDE. That is what you are doing is, in this particular example, the author of the problem had taken this particular GDE combination. That is this combination. This is he had taken. Here it is consisting of star network. This star network is going to convert it into the delta. So then what will happen? You will get one resistor like this, one resistor between E and D, and one more between G and D. You will get like this. Okay, middle one will be vanished. Then it will be okay to simplify. Okay, that is the technique he is applying. Clear? Now, In the next two slides, we'll show you that simplification. GDE, that is converted into star, is converted into delta now. Now, once the star is converted into delta, then this circuit will become like this. Now, this 15 in parallel with 3, this 5 is in parallel with 4, and remaining these 3. These 3 are delta. Now, if you simplify, further, the circuit will become like this. Now, again, here you are having two delta connections and two star connections. You can take, if you convert one of them, automatically the problem will be simplified. If you've taken 5, 8 and 20.9 and convert it into equivalent delta, it will be over. Otherwise, you can take 1 ohms, 5 ohms and 2.5 ohms and convert it into delta. Okay, so if you do like that, then you will get a simplified network. A simplified network will be like this. Now, from this diagram, between A to B, you can easily calculate the equivalent resistance. The answer for this question is 10 ohms. These are just for example purposes only, applications of this conversion techniques. Clear? So now this is what about the summary of star to delta and delta to star connections. The practical applications of star to delta and delta to star conversions is in the motor starters. In some of the induction motor starters, we will use the star to delta conversion. And similarly, the windings of the three-phase generator are connected in star. Okay, the transmission lines are generally connected in the uh, delta connection. Okay, whereas for the distribution side, they are connected in the star. Okay, so this particular problem I am giving you to the example. You need to do the homework like, and you need to get the answer. Okay, here the technique is, first these two are in series. Okay, and you can take this combination consisting of 34 ohms, 30 ohms, 30 ohms. These three are in series in star connection. You can convert directly into the delta. Okay, after that you need to convert one more, that is star 12, 12 and 10 equivalent with this particular branch. You can convert it into the delta again, then automatically problem will be solved. So thank you. This is today's explanation. We will see some more time with another explanation. Thank you.